this object in 4 dimensions. This rigid object, which was perfectly stationary, 4-dimensional object, has now been experienced by this little film. And in fact, a great deal of its geometry can be understood by dwelling on this, just like the Flatlander, if they were so inclined, could understand a lot about this cube they were looking at by understanding their movie. And these analogies and metaphors are very important for getting our initial glimpses into 4th dimension. And in fact, we're looking at probably the one that is the most common way to introduce 4th dimensions now, and is, of course, time.
Yeah, and I think Maggie is also going to use time to help us see 4 dimensions. So let's go take a look.
Great.
In 1910, Scientific American held a contest asking readers to describe the 4th dimension. The 15 winning entries went into great detail about a 4th spatial dimension. But not one entry mentioned the other 4th dimension, the dimension of time. Albert Einstein changed all that when he put forth his theory of relativity. Einstein said you can't talk about space without dealing with time. Looks like Maggie has an appointment at the dating service, which appears to be on the corner of X and Y. She needs to go up to the mezzanine level and be there by 1 o'clock.
Hi, I'm here for the speed dating.
I'm sorry, it started at 1 o'clock.
But since Maggie has arrived 30 minutes late, she's got the wrong coordinate in the time dimension. And her online dream date just walked out the door with someone who showed up on time.
So the 4th dimension, time, I don't know, maybe. But in fact, as far as a mathematician's concerned, it could sort of be any kind of statistic, right? It could be height, weight, I mean, whatever you like. I mean, any parameter, so to speak.
Yeah, you're free to have 30 of them, 30 of these parameters. You're in some big, 30-dimensional space where your coordinates and your parameters.
Not even you can see.
Yes, and in fact, in some ways, C is kind of the wrong thing, and part of that's because these things might have very different sorts of units. I mean, like space, it's all in the same unit of measurement, and so you can do all kinds of cohesive things, make measurements, and do things that are across these dimensions in a sensible way. And there are notions of dimension that have everything to do with that. Objects living in a place where there really are units.
I see. So we're going from a notion of dimension as simply number of parameters to almost a measurement.
Maybe we should start with a simple example. Okay. We're gonna imagine that I have a ruler.
Okay.
And my ruler is a foot long.
Okay.
And you have a yardstick.
Okay.
Let's build a line.
Okay. So my line is 3 times as long as your line.
That's right. So now let's build a square.
If I use 20 rulers and you use 20 rulers, I've still got a line 3 times as long as your line.
That's right. So these things are going to scale perfectly. So now let's suppose that you go ahead and make a square out of your yardstick with one of your units on each side. So
okay. Great.
And we have this square here.
Great.
And now my question is, I'm going to build the same thing, but in my units, I have this foot-long ruler.
Right. So my square is 9 times as big as your square.
That's right. Your square is 9 times as big, or 3 squared. The line was 3 times as big. This is 3 squared.
Right.
Now that notion of dimension, this square that's coming in, is our next notion of dimension.
2-dimensional square in my.
That's right.
In my
How many more of my object would it take to fill yours? It's a spatial notion. Let's build a cube.
Okay.
Okay?
Okay.
Now, here's your big cube and my little cube. And this is a problem, that people that make statues run into all the time. How many of mine are going to be taken to put inside of yours, or what is it?
Right. And I'm betting it's going to be 3 cubed.
That's right.
Because my ruler is 3 times as large, and I'm going in 3 dimensions now, so it's going to be 3 to the 3. So 27 of your cubes are going to be in mine.
So we have these 27 cubes filling up that space.
Right.
And this is a very important thing, the way that an object scale, how it's scaling with sides. If I make my ruler 3 times as big, it takes 27 times as much. Here's a fun one that brings us back to where we were before. Let's take a hypercube. You're going to build a
hypercube out of a yardstick,
Out of a yardstick. So you're some 4-dimensional being who has this luxury. You've built the hypercube, and now we're kind of used to looking at this picture.
All right, there it is. There it is. So I'm going to guess, that I'm going to need 3 raised to the 4th power of your hypercubes to fill up my hypercube.
That's
so 3 to the 4th is 81. So that's my guess.
And let's watch 81 of my cubes fill up your hypercube. So it's
all true. I couldn't have seen it, but it's all true.
And this notion that we're using an analogy to understand dimension is going to be very powerful for our next understanding, because we've just gone through some nice friendly dimensional accounts. Let's build something a little bit more interesting. Let's build a snowflake, something called a Koch snowflake. So what I'm going to first have you do is take your yardstick and build an equilateral triangle. All the sides are the same.
That I can do.
That we can do.
Yes.
And now I'm going to have you take each side of that and split it into 3 equal-sized pieces, which now happen to be the size of my ruler because there's 3 feet in your yard.
Right.
You're going to take that middle piece and you're going to remove it.
Okay.
And you're going to replace it with the edges of the equilateral triangle that would have that as a base. So now we see this little star thing.
I'm adding more points. Yep.
So it's more complicated, nowhere near what you might think of as a snowflake.
Right.
But now we're going to do something in mathematics we call iterate. It means we're going to repeat this process.
Okay.
So you're going to take each one of your edges and you're going to do that again. You're going to remove the middle piece, and now you're going to do something that mathematicians like to do. You're just going to do it forever.
Right. That is the mathematician's credo. Take it to infinity.
That's right. We love limits. And this snowflake here, now we're going to be playing a similar game as ask, I'm going to build the same snowflake but using my ruler.
They seem to only differ in scale.
They seem to. Now let's see. Before your line took 3 of my lines, your square took 9 of my squares. Let's see how many of my snowflakes it takes to fill on top of yours. Now, fortunately, the side of your snowflake, the iterative construction, looked exactly like mine because you were 1/3 the length after one step.
Right.
So I can unfold my snowflake and put it on top of yours, and I don't cover much of it. I cover, well, about 1/4 of it.
Right.
And if I built 3 more, and I put them
unfolded those,
I see I've filled your snowflake with 4 of mine.
Right.
So now we're in a funny thing. The line took 3 of mine.
That's right.
The square took 9.
Right.
And now I have 4, which lies between 3 and 9.
Right. And so now what we're interested in is that sort of relation. So 3 to 9 is a relation of squared, but 3 to 4 is actually a relation of a fractional power.
That's right. Right now we want
something in between 1 and 2.
That's right. We need that 4 is equal to 3 raised to the dimension.
Right.
Okay? And we need to find that dimension.
Right.
Well, that requires solving that equation. And fortunately, with mathematics, we can solve that equation, and we get something like 1 1/4 dimensions, some fractional dimension.
Right.
So this gives us a sense that dimensions don't necessarily have to be integers, and this notion of dimension is very powerful in all sorts of ways.
Fractional dimension, or the short is fractal.
That's right. This is called a fractal.
So this is an example of a fractal. Life is fractal, in fact.
That's right.
That's right. And in fact, fractals are used to create, all sorts of computer graphics, not just this snowflake here. So all sorts of things that look lifelike in some sense. Mountain ranges, sea coasts, all those things look kind of fractal. So, Greg, thanks a lot for the explanation, and we're actually going to see it in action right now.
Great. Okay. My pleasure being here. Thanks for inviting me, Danny.
Great.
My name is Carl Richter. I work at Leica House. I'm a technical director. Leica is a production company in Portland. I work in the House division, which does television commercials. We do CG commercials, which is computer animation, as well as stop motion animation and hand-drawn cell animation as well. My particular role is to really bring other people's ideas to life. And so, a director will come to me and explain their vision for what's going to happen, and then, my job is to really realize that and make it exactly how he wants it to be. Being as we use computers to generate all of our computer graphic elements, all of these engines are driven by math. One of the simplest examples of how we use fractals is called fractal noise. Fractal noise is just like kind of an organic pattern that we can introduce to an element to make it seem more natural. Things like this might be like mountains. If you look at a mountain range, you can see like big mountains, but then when you look closer, there's like smaller mountains. Another thing that is like this are clouds. They'll have like very big details and very small details. Fractals are perfect for describing something like this. I already have like a small cloud bank here that I've set up, and basically what this is doing is this is running a fractal algorithm in a 3D space, and we're just kind of taking and looking at a little cross section of this 3D space. If we go into the texture part, this section right here defines the actual equation that's being used to generate these clouds, and this is a fractal equation that this three-dimensional space is kind of taking a slice out of. To illustrate this, if the texture isn't being applied at all, it looks basically like this flat, uniform fog bank. And the more I turn up the area where these, basically the negative space that this algorithm is describing, the more these clouds are kind of revealed. This is a short that the studio did called Dream for Hokusai, and it's primarily stop motion. After we were done doing all the stop motion animation, they handed it over to me to add some computer graphic effects. The first thing I added was this mist that comes in over this water. And this water is actually just a piece of mylar that's been stretched out across this table here. And this mist was added using the same kind of fractal noise that we were using to do the clouds. I just added kind of like some subtle upward velocity to it and some better lighting as well. As we zoom into the forest and these samurais that are fighting, you know, there's these leaves that were added in. The motion of these leaves fluttering as he's like swiping his sword is all defined by using a turbulent noise field, which is basically using fractal noise to interfere with the vectors of each one of these leaves to give it this natural kind of fluttering motion. I think the whole idea of this animation was to bring these paintings to life and to kind of imagine what happened, you know, in between like this early morning and then this winter night shot. I really like the whole idea that we're kind of creating stuff from nothing in a way. For me, it's really exciting to bring to life, you know, elements that, you know, really like don't even exist. It's awesome that we're able to bend math to such artistic ends.
In today's high-tech world of special effects, video games, and virtual reality, the mathematics of dimension has, well, taken on new dimensions, as fractals have become an important method of generating realism in complex natural objects for animators. Still, understanding dimension is truly a powerful means of experiencing our real world in ways that help us solve great mysteries like the nature of time and space, and simple problems like finding the right date. So what's the answer? Is this real or just science fiction? I can't tell you for sure, but one thing I can say is that in the world of mathematics, higher dimensions aren't fiction at all. They are reality.